I want you to imagine you're driving on the road. Okay. So when you're driving on the road, there's a lot of relevant information that you need to know about other agents in order to play optimally. For example, you need to know how other agents interpret traffic signals, and you need to know what side of the road they're going to drive on. But there's oftentimes lots more information in these sorts of games that you don't need to know. For example, when you're driving, you don't need to know what other drivers' final destination is. You don't need to know what their low-level motor controls are. And you definitely don't need to know things like what your music taste is, what they're listening to on the radio. This sort of information can be discarded. So in this work, we're interested in formally capturing this dichotomy between strategically relevant and irrelevant details. So essentially the way we do this is in terms of this mathematical object that we call the strategic equivalence relation. It's captured by this image here at the top. So the main idea behind the strategic equivalence relation is that I want you to imagine that we're playing a game together, okay? And what I'm going to do is I'm going to partition your strategy space based on the best responses that they induce for me. So on the left-hand side here, we have the strategy space for you. And on the right-hand side, we have the strategy space for me. And we're mapping your policies to best responses from me. So what this does is it partitions the strategy space on the left, so this is your strategy space, based on the best response that they induce on the right. So for example, all the policies here in pi2 induce this as a best response. So the best response is a set valued function. It might be multiple strategies. But all the strategies here have the same best response. And the intuition here is that two strategies that differ only on strategically irrelevant details fall in the same block of the partition because they induce the same best response for me. If two strategies differ on some strategically irrelevant detail, it must mean that they induce some different best response, which means that they fall into two different blocks of the partition. So what this strategic equivalence relation does is it captures the minimal amount of information that I need to know about your strategy space in order to formulate what my best response is. So we can compute this strategic equivalence relation in some simple normal form games like this down here. So this is a normal form game between player X and player Y, and they share a common payoff. So we only put one number in each of the squares down here. So here we're going to compute the strategic equivalence relation for player Y. So we're considering the mapping from player Y's strategy space on the left to player X's strategy space on the right. And we're going to partition player Y's strategy space. So on the right-hand side here, we have player Y's strategy space. This is a probability simplex over the actions D, C, and E. And each point in here represents a mixed strategy over these three actions.
So in this case, like the blue player has like strictly different strategy optimal than like the red player.
Exactly. So yeah, any strategies in the blue space induce B as a best response. And any strategies in the red space induce A as a best response from player X. And then in the middle, we have this one-dimensional separating line in green, where both A and B are a best response. So immediately you can see we've reduced this continuous space of strategies for player Y on the right down to just 3 different classes. And these 3 classes capture the relevant information in this case. But really, the real magic happens when we do this in sequential games. And in order to compute the strategic equivalence relation in sequential games, we have this Bellman backup. It's essentially a dynamic programming operator that relates the strategically relevant information at some state S to the strategically relevant information in future time steps. Sort of like a value iteration update, like a Bellman backup. And what this lets us do is it allows us to compute the strategic equivalence relation in sequential games using dynamic programming. So that's what we did in environments like Overcooked. And one of the cool results that we found is that when we compute the strategic equivalence relation over the full strategy space of history-dependent strategies, in Overcooked, we often found that the space of the strategic equivalence relation is very simple, meaning that we only had very few classes. In fact, we oftentimes had to engineer some kind of symmetry in the environment to create different strategic equivalence classes. What do we do? So in this environment here, the agents are trying to just collect onions and put them into pots without getting into each other's way. And the fastest way to get the onions here is through this central square. but both agents can't occupy the central square at the same time. If they both try to do that, then they'll collide and there'll be a no op. So in order for the agents to play optimally here, they need to agree on which agent gets to occupy the central square first. And then the second agent will follow or potentially go around the perimeter. And as long as these agents can share this one bit of information before the game starts, then they can play optimally. But these are the only single piece of strategic information in this game. And if you scan this QR code here, you can go to our website. We have some exciting other results. Here we have some GIFs of the equivalence relation in this environment. And we have some other interesting environments like this one here. Here, agents are trying to collaboratively get an onion and a tomato into the same pot. And one really interesting result that we found here is that there's actually only one strategic equivalence class here. We actually thought there was a bug in our algorithm at the beginning when we saw this. We were expecting there to be multiple classes, potentially differing on which agent gets which vegetable, or how the agents go around the central pillar without running into each other, or what pot they deposit the vegetables in. But actually, all these strategies fall in the same equivalence class, meaning the agents don't need to exchange any information before the game starts, and they can still play optimally. So strategic equivalence relations, they let you analyze multi-agent games like Overcooked and figure out the degree of coordination and the different types of coordinations that agents need to use in those sorts of environments. And sort of almost as a side effect, we sped up the state-of-the-art algorithm for computing optimal policies in DECPOM DPs. So we took the optimal algorithm here the state-of-the-art algorithm for computing optimal policies in DECPOM DPs, and we essentially just put strategic equivalence relations on top of them. And the reason we got such a dramatic speed up is because we were able to group strategies that induce the same best response into one single object, meaning that we were able to operate over a much lower dimensional object of the strategic equivalence relation rather than the full strategy space. And as you might expect, the less coordination that's required in the game, the fewer equivalence classes we will have, and the bigger computational speed up we'll get using strategic equivalence classes in these sorts of algorithms.
So is the basic idea that because you did this grouping here by equivalence classes, you only have 3x3 matrices, and so it's much easier to compute the space?
Essentially, that's exactly right. You can think of it as doing state abstraction for solving MDPs, right? Grouping together similar states. Here we're essentially grouping together similar actions that induce the same best responses.
What's the biggest environment you tested on? Is it Overcooked, or do you have plans on bigger environments?
So right now, because we're computing optimal policies in DECPOM DPs, which is very expensive even with our speed up, we're only able to scale up to these sorts of overcooked environments up to a horizon of around 20 or so. I think that takes about an hour. But that's in relatively simple overcooked environments. We're really excited about future directions, and we hope some other people might build on this work too, of approximating these equivalence classes using learning algorithms in larger games. We have a lot of ideas revolving around that too that we're excited about. And I think being able to scale up to larger environments and approximate these classes is a really exciting direction. Thank you.
I'm here with Matthew Farrugia-Roberts, and author of the Invariance in Policy Optimization and Partial Identifiability in Real Learning paper. Do you wanna explain quickly what the paper is about?
Yeah, sure. Thanks. So people will be familiar with reinforcement learning, which is obviously where you want to get a software system to have some behavior, and to specify the task, you need to design a reward function. But that reward function for a complex task can be very hard to design in a way that is not hackable, or it can incentivize the wrong behaviors. Especially if it's a complex motor control task, like doing a backflip, for example. Or in the sort of more ambitious sense, if you want to encode human values writ large into a reward reinforcement learning system and have it optimize those, it seems impossible that we could ever write that reward function down. So people turn to reward learning, which is the idea that you can just use data from agents, like humans, for example. You can observe their behavior, you can ask them to compare behaviors and evaluate them, and then you can use that as a data set and learn a reward function as like a statistical problem where the reward function is like a latent variable that describes the behavior. So that's the setting that we want to study. This is a theoretical paper where we look at that statistical problem of learning a reward function from behavioral data, and we observe, it's actually well known, but we want to sort of formally study the fact that it's a partially identifiable statistical problem. So what that means is you can have multiple reward functions that when you have your hypothetical model that says how those reward functions lead to behavior, there could be multiple reward functions that lead to the same behavior, like the same preferences over trajectories, if you're thinking about RLHF or something like that. So our main contribution was to kind of study a bunch of different data sources that you could have and to figure out which reward functions lead to indistinguishable data like that. So you have like a space of reward functions, and you have certain sets of reward functions within that space where all of the reward functions in that set all lead to the same observable behavior. So that's an identifiability problem, because if you then want to learn which reward function generated your data, you can't figure out within this set which one it was. Does that make sense?
Yeah. So, like the main goal is to have like AI like understand, like internally explain human behavior, right? So you have like a human like doing a task,
Yeah.
and the AI is trying to like understand why the human did this, or like what like drives human behavior or something. And so why would you want to like recover like exactly the precise reward function if you could like if you could have the same behavior with this different reward functions? Like, why do you need to have the precise one?
Well, you don't always need to know precisely the reward function. It kind of depends on what data source you start with and what your objective is to do with the reward function that you learn. Because that's the setting, is we've got data, we want to learn a reward function, we want to, like you say, use that for something. Like, for example, we want to optimize it or something like that. So
basically, a concrete example would be like have a robot do exactly the same as a human. Like, you have a human like doing a job, and you want the AI to do the same job as the human with the same like preferences over the actions.
Yeah. In that setting, I think that this identifiability problem is not going to be a problem, and the reason is because you'll do your statistical problem, and you could be anywhere within this set, but everything in that set, when you do the reinforcement learning, gets you back to the same behavior anyway. So that's an example where you have precisely the right kind of information about the reward function, and you don't actually need any more information about it.
So what's a setting where you would need like more information?
One example is that if you wanted to learn from an agent or a human acting in one environment, you wanted to learn a reward function, and then you wanted to optimize that reward function in a slightly different environment. Maybe the transition dynamics are different, or the discount rate is different. If you want to do that kind of environmental transfer, then you can start to see that the set of reward functions you got, some of the reward functions in here lead to different behaviors if you optimize them in the next one. So it matters which one you pick.
And so you talk about like different data sources, and I see there you have like this poster. Like,
yeah.
What are some like kind of like different data sources?
Yeah. So, well, I mean, each of these boxes in the diagram kind of corresponds to some specific set of assumptions, like whether you have a certain type of optimal policy or a different type of optimal policy. But broadly speaking, we've got sort of over here, we've got what you could call inverse reinforcement learning data sets, where it's about optimal behavior from some expert, some definition of optimal. Whereas over on this other side of the diagram, you've got data sources that are based on preferences between trajectories or distributions between trajectories. And you might have different assumptions about how those preferences are generated, whether there's Boltzmann decision noise in the human evaluators, or whether they're picking the precisely optimal preference according to its return in every example. So I guess the idea of this figure is that each of these data sources has a different, there are different sets of reward functions that will lead to the same thing. And you'll end up with, in general, like a partition of the reward space, where each group in the partition leads to like the same set of preferences in this case, or
so is this
behavior over here.
This diagram here where like you have like different rewards being like in the same box or something?
Yeah, that's right. So if you look here, you could see this would be an example of a partition of the space of reward functions, where everything in this rectangle could be maybe lead to the same optimal policy, whereas everything in this rectangle leads to a different optimal policy if that's the reward function.
And so this one is like a bigger partition where like if you're if two things are in the same partition here, they will be in the same partition here.
That's exactly right. Yeah, so you can see the two rectangles that I talked about before correspond to this weird shape over here. And in general, I set up this figure to illustrate that. You can always make these bigger shapes out of a selection of these smaller shapes. So this is how you compare partitions. This is called partition refinement. In this case, this is the finer partition.
Is there like any goal of like having like different partitions? Like, is there like any better partition for different problems?
Yeah, well, this gets back to what you were asking about before. So the setting where you want to know how much reward information do you need for what you want to do with the reward function. That's also a problem you can formalize with a partition. So you can say, what are all of, if I want an optimal policy, what are all of the reward functions that are going to lead to that same optimal policy? This is going to give you another partition. And then you can compare the partitions like this with refinement. And the condition, the sort of takeaway is that you will have enough information about the reward function if and only if your data source that you're learning from, the partition for that, is a refinement of the partition for your sort of objective, what you want to do downstream with the reward function. So in order to determine if you have enough information about the reward function, you just compare partitions. That's sort of the framework level contribution of this, is that partitions are like, mapping out the relationships between these partitions is useful if you want to answer questions like, does my data source contain enough information about the reward function for what I want to do with it? Does that make sense?
Yeah. Thank you very much. I think that was a great presentation.
Great.
Hi, my name is Andrew Szot. I'm a PhD student at Georgia Tech. And in this work, we study the problem of how agents can cooperate with unseen agents in cooperative rearrangement tasks. So in the problem setup, we have this blue robot here that was maybe trained to only cooperate with the red agent at training time. But then the question we ask is how the blue robot can then generalize to cooperating with an unseen green agent at evaluation time. So it never saw the green agent during training, and perhaps the green agent has unseen coordination strategies that we're not familiar with. We study this problem in the context of object rearrangement, where robots need to rearrange objects from a start to a goal position. And the key aspects of our work is we introduce a new method to solve this problem called behavioral diversity play. We introduce a new benchmark called the social rearrangement benchmark for studying this problem, which features egocentric visual observations, and it's a cooperative task where robots need to rearrange objects as efficiently as possible.
It's kind of like very similar to you're in a kitchen with your friends and you don't know how to like tidy their kitchen. Is it like the idea behind your work?
Yeah. I don't know if you've ever played the game Overcooked before.
Yeah, I've heard of it, yeah.
Yeah, so the setup is actually very similar to Overcooked, and that was one of my key inspirations for this. Is in Overcooked, you have this chaotic kitchen environment, and oftentimes there's this unspoken coordination of you observe whatever your friend or your other player is doing, and you have to adapt to that to help complete the task as fast as possible. And it's the same setup here, where these robots are only operating from like egocentric visual observation, so they only see the view from their head camera. And based off this information, they need to adapt to whatever their partner is doing. So maybe you see your partner is going into the kitchen, you have to adapt to that, maybe move out of the way so you don't collide. You maybe see they're grabbing the apple, so you help out by grabbing the bowl. So it's all about adapting to what your partner is doing.
And like intuitively, like how do you make those like robots like in the game like cooperate or like adapt to the?
Yeah. So that's the key thing of our paper, is introducing the new behavioral diversity play method. So the way this method works is we have this two-stage training approach, where first we learn a behavior policy that is trained to generate all sorts of different diverse behaviors. So the behavior policy is kind of trying to generate the entire distribution of possible cooperation strategies we'll run into at evaluation time. Then we freeze this and now train a coordination policy to train against all these different behaviors that the behavior policy can generate. So the idea is then, by training against all these different diverse behaviors, the coordination policy should be very robust to anything a partner might do. Now, at evaluation time, hopefully these unseen policies that we did not train with will lie within the distribution generated by the behavior policy, and we'll be able to generalize this new behavior.
So basically, like your behavioral policy is kind of the off policy in RL, where you like have like a random thing that like explores like all the like action and observation pairs and.
Yeah, it needs to have this diversity, but the tricky thing about this problem setting is it's visually realistic, or it's visually high dimensional, and it's a very long horizon problem. So just doing random things is not enough. And that's what our method does, is we have both a task objective for actually completing this long horizon task, but we also have this new diversity objective for actually encouraging the agents to complete the task in different ways.
Like trying out different ways of tidying the kitchen so that you see like if
Yeah.
you like match with your friend.
I mean, yeah, exactly. So the behavior policy will learn all sorts of random stuff. Like it might learn to, I don't know, open up the drawer, pick up the apple, place it on the counter, put it back in the drawer, and put it on the table or something like that. This objective here is trying to encourage the robot to just do everything. Because the key thing is we want our coordination policy to be super robust to adapting to any sort of behavior that our behavior policy will throw at us.
And what's the like observation space? Is it like kind of like very specific like 2D things, or is it like actual like continuous images, or?
It's just the image. So it's just the onboard image the robot has on its head, and that's it.
And in terms of like actions, is it like do you have the macro action of like open drawer, or is it like?
Yeah, so we do have some macro, like we operate over macro actions like what you're saying. They have kind of these primitives, opening drawers, moving around. But even with this abstracted action space, we find that like we really need to scale up training to get any sort of meaningful behaviors out of these policies. And that's also why we use the habitat simulation platform for this, because we could really scale up visual RL in this problem setting. Yeah, and so what we find is that, prior baselines in this space do well when they have a perfect representation of the state, when things are fully observable, but they really break down when we move to the more realistic, egocentric visual observation space. Whereas our method, BDP, the behavioral diversity play I talked about before, generalizes a lot better to where operating from the egocentric visual camera. And we find this coordination agent can do all sorts of interesting things, like it will kind of look at what its partner is doing to see how it should react. It'll do things like back away from the kitchen, which is like a very cramped space. If the other agent's coming in, it'll see what other objects the other agent's rearranging and like adapt by rearranging other objects to like divide and conquer.
Very, very human-like.
Yeah, exactly. And all these things are just emerging through this kind of diversity objective plus coordination strategy. So,
what's the like next step? Like I assume this paper was like submitted like a few months ago.
Yeah, exactly. Yeah. So yeah, we see this as kind of a stepping stone for moving on to robot-human coordination. So the more realistic setting is where we have a robot that's helping a human, hopefully in the real world, not just in simulation, and then the robot actually has to adapt to the much more diverse behaviors that a human might exhibit, and be able to help the human in like everyday house tasks, like helping around the house or tidying up or anything like that.
Oh yeah, then thank you very much.
Thanks.
I'm here with Fangchen Liu,
Yeah.
who has a paper kind of related to alignment because they're trying to replace the RL in RLHF by something else. Do you want to explain your paper to people?
Okay. We propose a simple, novel, and effective RL-free alternative to RLHF just by cleverly relabel the instruction from the feedback and do instruction fine-tuning on the LLM. And in this way, we are able to surpass the RLHF by a large margin and also surpass supervised fine-tuning on some big bench reasoning tasks. So the way we do it is very simple. So at the very beginning, we give the model a prompt, give a correct answer to this problem, and then we take a query problem from the training set and let the LLM to generate some answers. And after that, we evaluate the answer's correctness by checking the LLM's output with the answer in the training set and tell the model whether the answer is correct or wrong. So the way we do it is if the answer is correct, we didn't do anything about the instruction, but if the answer is wrong, we relabel the instruction to be give a wrong answer of this problem. In this way, we got a data set that is aligned by turning the feedback to instruction, and then we can train the LLM again on this data set and then run iteration of that. And after that, we are able to improve our model on a variety of big bench reasoning tasks and surpass RLHF supervised fine-tuning. And we argue that this is a very general framework, not only limited to the reasoning task, even if we are only doing binary feedback and scripted feedback in our paper, but we can definitely have some more powerful base model in the future, and maybe some reward models provided by some other companies that tell how well the output of language models and it's aligned with the instruction. For example, here can be a reward score that tells you how well your alignment, how well your output is aligned with the instruction, and you just relabel the instruction to be give an output that is have a reward score of 0.9, give an output of a reward score of 0.2, and then you retrain everything in supervised fine tuning. And our method can utilize all the successful data and failure data, and without training additional rewards, additional value function. And you can see its comparison with previous method. It's a very simple and effective way of doing learning from feedback using pure supervised fine tuning.
Yeah, I guess like one thing I don't understand is at the beginning you say to like give correct answer, and what's the part where you like relabel it? Is it like you generate the feedback with like, is it like humans that do it, or is it like?
It's scripted, so we just give the model, give a correct answer, give a question of the model. The model is giving some answer to the question, but however it can be wrong. We just evaluate whether it's correct or wrong by checking with the training data set answer.
Oh, okay.
So we just do some scripted function checking. We just write some program to check that. So no human labor is in the loop. But definitely in the future, if someone can hire some contractors, you are able to provide some human feedback in the loop, which also is just a general framework. But for reasoning tasks, definitely no need to do that because we can know the answer is correct or wrong by checking the answer in the data set.
And so you use this like data set answers, like these labels, to give feedback?
To give feedback.
Text?
Yeah. Give it feedback and turn that into instruction. And during evaluation, we always ask the model to give a correct answer. But during training, we just make the model know like which part of the data is aligned, which part of the data is not aligned. We just train the model on both kind of data and make the model aware or distinguish from the right answer to the wrong answer.
What kind of models did you use, like in terms of like language model, like what size of models, or?
We are using Fangchen large. At the time the paper was submitted, and some because the computation resource is not affordable for us to train more powerful models, so we just to train Fangchen large. There is Fangchen XL, but we are not able to train that. So yeah. But currently we have Llama and Llama 2. Maybe we can extend this framework on some open-ended dialogue task and change this score to be some alignment score or quality toxicity score, something like that, and using the framework again.
And do you think like the alignment score is it like higher than like using RLHF, or?
I think actually this actually at least it's easily to train or implement because RLHF requires you train a reward model, train a value function, and tune the PPO. Actually, a lot of hyperparameters are digital training loop. For ours, you just take the original training loop, add in some by prompting the model, relabel the instruction, change the data set a little bit, and then you just train everything very easy. So you can just examine whether this work or not on your task very easily. And I would say it's kind of equivalent to do something like RHF. So for RHF, you always have this score, and you optimize the value and policy on that. But for ours, you can already tell the model. You can just tell the model how well you perform or how much score you're able to obtain for your answer. So just like how human learn, like the teacher tells you everything in language, like how well you perform, something like that.
You can give feedback directly to the model.
And also for RLHF, the assumption is like you should model everything. You just scalar reward as your feedback. But sometimes the feedback can be more fine-grained. It's hard to be represented as a scalar reward. So in that sense, maybe it's better to describe the feedback in your language and prompt the model to know some fine-grained details about the feedback. Because like sometimes the people for some dialogue tasks, it can be like the feedback can be you are making some factual error and which sentence you are wrong and how it can be corrected. This is something hard to be represented by a scalar reward. So in that sense, maybe by prompting the model and doing instruction fine-tuning is a better choice.
Thank you very much. I'm here with Dongyoung Go, who's the author on aligning language models with preferences through f-divergence minimization. So yeah, go to the...
Yeah, hi, nice to meet you. So Dan, can I give you a brief introduction to this?
Yeah, go for it.
Yeah, so here what I'm trying to do is just give some distributional interpretation to this RLHF method or other alignment language model, and then also generalize it to further objective function. So maybe a lot of you might be a bit familiar with this RLHF, which stands for reinforcement learning from human feedback, which just firstly define the reward classifier as a preference, and then maximizing it with some KL penalty. But the thing is that the RLHF can be interpreted in the distributional approach. So they cyclically, I mean implicitly, define the target distribution and then minimize the liberal scale divergence. So that's why this is the way they train neural network pi theta to approximate the P-RLHF. But there's another interesting line of the work which is called GDC, which also define the target distribution and then minimizing the 4K divergence. So these two looks very different, but in this terms of view, the only difference is the objective function. The one is minimizing the liberal scale divergence, and the other one is minimizing the 4K divergence. So here, our research question is whether we can generalize it to other kinds of objective, or whether this different objective have different impact on the training language model. And in this theorem, we can see that actually, yes, we can generalize it to other kinds of objective. Here, we say that using FDPG, we can actually minimize any kind of objective in the f-divergence family. Here, f-divergence is the kind of divergence family of two distribution, which can include 4KL, reverse KL, and also total variation, Jensen Shadon, and any other infinite kinds of example. So by just plugging this column to this formula, you can actually recover existing RLHF or GDC with some alignment score. And this is how we,
How do you define alignment score?
Yeah, alignment score depends on very different tasks, but basically here we are using just RX as on some kind of abuse of the notation to represent the score of the classifier function, classifier score. So in fact, there's kind of a lot of different notation like E pi or EBX for the alignment score, but for the simplicity, I just use the word alignment score as some kind of integrated term. And the thing is that in the experiment, these two or other different objectives have some different impact on the final train model. So here you can focus these two lines. One is red line and the one other is the blue line. The red line is the minimizing reverse KL divergence, and blue line is minimizing the 4K divergence. So you can just treat it as a RLHF as a red line and GDC as a blue line. And here you can see that while the training epoch goes on, the liberal scale divergence of the red line shows very great drop of the liberal scale, which is quite intuitive because RLHF actually does minimize the liberal scale divergence as an objective. But the thing is that they actually fail to minimize the other metrics of the divergence. So minimizing liberal scale divergence does not minimize other kinds of divergence. For example, like 4KL or TBD or Jensen Shadon divergence, they cannot minimize the liberal scale.
Do you have like any intuition for those those three metrics? Like what do they mean like for the model?
Three metrics?
Like what does those divergence mean for like in practice?
Yeah. So these four are just four different approach of how distinct our current neural network is from our target distribution. For example, the liberal scale and 4KL have quite different two distinct property. Liberal scale is focused on how well they capture the mode, and the 4KL focus on how well they cover the whole domain.
Okay.
Yeah. So for example, if we can imagine that like for this target distribution, there could be a lot of mode. While we can actually quantify it, but we can just imagine there could be a lot of mode. But for the while we're using the liberal scale as an objective, we can just focus on one kind of mode. That's the kind of typical property of the liberal scale divergence.
And the experiment like sentiment preference and lexical constraints. How do you explain it, like simply or?
Oh yeah, this here I just used the RX as a sentiment classifier to just here the experiment. The task is to generate the positive sentence. Yeah.
So something that is classified as good sentiment, like this is good.
Right. I just used the popular pre-trained sentiment classifier as a reverse score, and here is whether the generated sentence include the target word, something like restaurant or amusement or Wikileaks, which have quite a different frequency from the original pre-trained language model. And in our full paper, there's a bunch of other different experiments, which include conditional generation, which means detoxifying, and other things like gender balancing. And yeah, just to jump into other question. here the reverse KL just failed to preserving the entropy of the pre-trained language model. This is a kind of distributional term, but you can also check in the downstream measure like self-blue or distinct one. So you mind if I just jump into this table?
Yeah, go for it. Go for it.
So here, self-blue is a kind of similarity between the sentence. So how diverse the general sentence are, and the distinct one is the diversity within the sentence. How many tokens they use in the one sentence. And perplexity is how fluency the general sentence are, and the lower score means better score. Lower fluency means better fluency. And here we can focus in LKL, the last law. They have quite low perplexity, which means quite fluent, but they have quite high self-blue, which means they can be reasonable in generating one sentence, but they are not good at generating a lot of diverse sentences. So you can just imagine it like reverse KL just focus on one kind of mode from very different, from a lot of multiple modes. So as a final remark, we can just summarize it into a Pareto frontier of four experiments. Yeah. So here I summarize with the alignment score and entropy score of a lot of different experiments. And you can just focus on this alkane of the lead dot. Like they are, every time they are just positioned on the bottom right. So they have quite high alignment score, but less small value of the entropy. And as a contrastive thing, as a 4KL, they show very low alignment score, which means they fail to maximize the alignment score very well, but they are good at preserving the diversity, entropy. So you can just take it as a hyperparameter of the objective. If you want to try to focus on alignment score while you can just pay entropy as an alignment text, then you can just go for RKN and be happy. But if that's not your goal, then you can we just propose to use Jensen-Shannon as some replacement because they have quite good balance of this alignment score and entropy for every other experiment that we do. And actually, they are good at also in the Pareto frontier plot.
So it's the best one is the green one.
Yeah. Actually, it depends on a lot of experiment, but so you can just in either case you can just roll out to every kind of objective that you want to try on. But for the better, robust candidate, you can just focus on Jensen-Shannon divergence as a first objective.
Thank you very much.
Thank you.